And we are live. Hello.
Yeah, yeah.
So
Hello, Firefox.
today we're going to look at some algorithms.
I used Firefox today.
Oh yeah, what for?
Um, I was in the bell tower and we were setting up the simulation, and the simulation program we needed to update. And like, I
Hmm.
had a laptop, I had a hotspot, but I needed a USB device to transport it onto the computer. So I downloaded it, but it was like my internet was really slow, like flaky,
Hmm.
and it was like scanning it for viruses or something. The download, and like it was just not completing. I think it was like um, sending the file somewhere or something to be checked.
Is it on your
Uh,
phone?
yeah, it was like a organizational policy, and because that wasn't like completing, I just tried again in Firefox, and Firefox didn't do any checking, so like I just
When in doubt, use a different browser.
use a different application, and you'll get a different set of behaviors, which might work better for your use case.
I actually learned something quite interesting today. Did you know
Yeah.
that Tor was made by the Navy?
Well, it doesn't surprise me. The internet was.
Yeah. I mean, I knew it was like people think NSA and stuff, but no, it's the Navy.
Hmm.
Um, and obviously they sponsor it to keep it. I mean, I guess I'm talking about when it originally came up, um,
Mm-hmm.
and was developed kind of like the internet, and everyone who was using it wasn't malicious, but then, you know, criminals and stuff found their haven there. This is before crypto and stuff.
Is Tor like how is that basically black market stuff?
Tor is the browser of the internet such that it proxies your IP, and it's a way of hiding the user.
Yeah, that's what I mean. Is that basically black market access is you use Tor?
Yeah, they would use it because originally um, it wasn't designed for like websites, but then people figured out how to like host a website on that, I
Mm-hmm.
guess, channel of what would you even host on? But the main purpose was to not get their website machine traced back to
Mm-hmm.
any IP or any location.
Yeah, it's like extra anonymity.
Yeah, through the protocols that they use for routing and proxying and all that stuff, which would be worth trying to like doing like a session on. Like,
Hmm.
how does it kind of work?
Try it out.
Yeah.
There's
All right.
probably a subreddit of like stuff to do with Tor
Mm.
or something. Or see what people are doing.
So the main purpose of today is algorithms, and the strategy that we could do is just blindly search on GitHub and code review some algorithms. And what's an algorithm that you're interested in?
What does that say?
Algo code
Algo
review.
code. Yeah, okay.
I'm using my touchpad.
I reckon, yeah, let's do Heap.
Heap? Alright. Heap algorithm.
Look for like heap.h, I
Can you
reckon. We'll
Oh, you
find
want to do
some
it in C? Okay.
implementations.
There's Go. There's a repository for learning various heap exploitation
What?
techniques.
That's just the other Heap.
Yes, but still interesting.
Yeah, very interesting.
I will
Star that one.
add it to a Git repository, which I'm going to create for this, and submodule it. So we'll just like put like a bunch of like categories. So that could be in like reverse engineering, and then we have one for algorithms. And I'll just Git submodule. For those who don't understand Git submodule, How do you describe it?
It's like third-party repositories. It's basically Node package
Yeah.
with Git and with commit hashes as versions.
So it's like linking your repository with another repository that you can then check out on a particular commit when you submodule add it. Kubernetes. Why did I open that? Oh, okay, because that was a Go thing.
I'm cutting up a tomato, and it's really good. Like when you buy tomatoes from like Woolies and stuff,
Yes.
they're kind of tasteless. But this one, it's not like flavor, but it just tastes really fresh.
Uh-huh.
Yeah.
Okay.
I mean, this is the same tomatoes as the one that had a bit of mold. Like same batch. Like one of them was moldy, but the rest are like excellent.
Where'd you get it, sorry?
Haymarket, just like basically the same as Vic Market, but cheaper,
Yep.
more Asian.
Yeah, most of this stuff is on heap allocation.
Yeah, we want
Like we want heap tree
maybe look
algorithm.
for min heap.
Yeah, something like that. Oh, there's a bunch. Oh, yeah, here we go. Algo tree, C++.
Yes, collection. Yeah, see what they got.
Um, whatever. C++, algo, and terms. Oh, algo tree. Learning, mastering algorithms. It's in Chinese. More C++, heap tree algorithms. Support for D heap and B heap. What the hell is that?
I think what we want to focus on
Hmm.
is the same algorithm but like multiple repositories, so we can like compare them,
Yeah.
compare their APIs, compare their implementations. Are they like identical or do they do it completely different?
Okay, so you want like generic algorithm, Git repositories. The language was this in? Oh, whatever.
Even if it's different languages.
All right, I think
We got some, yeah.
we've got some. Most of it's C++, but
Mm-hmm.
that's fine. Algo, DS Algo 1. Okay. Okay. So let's have a look at what we got. We got this algo deck thing, and it has an MD file that describes heap. So let's just go through it.
Binary heap.
Binary heap, min heap or max heap, complexity. Oop. Insert, inserts. Insert is O log n. Well, that makes sense because we're doing divide and conquer type insertion for heap. I guess yeah. Let's review what our understanding of the heap is and see if it matches that
Yeah,
sort of
draw it
complexity.
out.
So heap representation would be a tree, a binary tree.
So let's have a few numbers, like a heap with the numbers 5, 6, 1,
Mhm.
3, or something.
But isn't it
What?
that the min heap would always have the smallest? So the min heap would always have your root node with the smallest number.
Yeah,
And then what would go to the left and right then?
bigger numbers.
So, and they would be ordered by.
the children is always bigger than the parents.
So if you say had like what you said, 1, 5, 2, 4, 10,
Mm-hmm.
how do you decide what's the children of the smallest? Because that could easily be 2 and 4.
Any combination, as long as it fits that constraint.
Okay. So we could get 2, 4 here, and then we could get 5 and oh wait, so it's not like binary trees where the left is smaller. It's
Yeah,
just that the root has to be smaller.
yeah, that's the only constraint.
Right. So if we have 7, yeah. So here's my heap tree. So I've got 1 at the top, 2, 4, 10 smaller than 2, 5 smaller than 2, and 7 smaller than 4. I mean, sorry, reverse what I just said. I guess a key feature to state is that it can be represented as a flat list or array.
Mm-hmm.
So you could represent this as 1, 2, 4, 10, 5, 7. And is there like empty nodes? So would I store here like some nil value, which I'll represent as this?
The empty nodes are in a certain location, like it goes left to right.
Yeah, right.
You fill it up left to right, top to
So
bottom.
it's got fixed size based on however many nodes, and the nodes will be the size of how many levels you've got. So if you've got like 1, 2, you would have 3, array of 3. If you've got 3 levels, you would have an array of 1, 2, 3, 4, 5, 6, 7. 7 items. So it's like 2 to the n minus 1 is the size constraint. And I guess we have to define then like a null value. And some languages have that.
Nah, you don't really. You just say where the end of the array is.
Yeah, I guess
The
I'm
array has
thinking
a
like
size,
if you're
and that
dealing with
implies all
like
the nulls.
C or something and you don't want it to be garbage, and also you don't want it like you got signed values or whatever. You want to give it some magic number to designate, right? To say it's
No,
empty.
you use a separate size value to say how big your array is.
No. I'm talking about when you have like an index that has nothing in it.
Oh, right. Well, okay.
Yeah.
It's right.
So you like languages like C or whatever don't have like it has null, but it's essentially 0. But what if the min heap actually can contain negative numbers? Like you don't want that. Because it would be treated like 0. And so you could say define a magic number for like negative infinity, which is just going to be like min of your t, which could be an integer or something. But you might want that value as well. So maybe like how would you do that in something like C where you assign
You could implement std option.
right in C? Yeah, you
Yep.
just create a struct. So an optional, what would an optional struct be like in C?
A bool and a value.
Oh, okay. Yeah, true. So you could just have a struct that has whether it has something, which is a bool. And how big is a bool?
1 char, 1 byte.
So 8 bits. And is that platform dependent?
Technically, yes.
So if you have a 64-bit machine,
no.
if you have a 64-bit machine, it's an 8-bit representation of in 64 bits, right?
No, it's still 1 byte.
Okay. So when is it technically no?
I'm not sure. But yeah, I think a byte can a byte be anything other than 8 bits?
Well, isn't that like based on the word size of your machine? Like,
Nah, I think the word size is like 64 or 32.
okay. Um, right.
Yeah, maybe if you wiki bytes, it might say if that's a variable or if it's always 8. I'm not sure, but in practical terms, it's always 8.
Yeah. I know this is sort of like the edge cases of
It's
what to
basically
really
if you're
know.
going to deal with a computer from 40 years ago, you might
Yeah.
have to.
The interface should always be the same though. So if you just assign a struct of bool and value, the
Yeah,
size representation
yeah.
should,
We're
at least
just
should be
talking about a
consistent.
bool. Like you don't care how many bits it takes. It's
Yeah.
like you only care about does it have at least one? Which yes, it has at least one.
Yeah. I was just wondering if there's like edge cases to that.
Hmm.
You know. Yeah, anyway. Oops. What are we doing?
Heap.
Yeah, that's true. Whoa, it actually does
Lol.
the Windows.
That was awesome.
Alright.
Ah, yeah, and the simulated computer was Windows XP, so it was like using Windows XP again since forever.
Yeah.
That was fun. I kind of miss the look of XP. It has a slight bit of skeuomorphism. And I don't mind that level of skeuomorphism.
Skeuomorphism. I have not heard that word before. Mm,
If you remember, like the taskbar and the start menu button, like it had a bit of
hmm.
depth to it,
Yeah,
a bit
right.
of reading and stuff. It wasn't just flat vectors like everything
Yeah.
is.
It's like when they went from 2D graphics and then to 3D.
Mm.
Yeah, that surrealness. Like they have to show off the 3D-ness, which was like shitty 3D, like graphics art.
Yeah, I like a small amount of skeuomorphism. I think it's good.
All right, so what's the API of the heap? Insertion, deletion, update,
Hmm. And I guess for completeness, you have read,
read.
reading the min val.
Oh, read, yeah. And this is a very common thing that you might see as like a CRUD.
Hmm.
Um, you know, if you're a web developer or something. Um, so how would you insert into so okay, so let's pretend like you are gonna go from scratch. You would potentially build your heap up, right? Um, and given like this set of numbers, can you still hear me by the way? Oh, hello, hello, no.
Sorry, I keep talking. I'm just washing celery, so it's a bit loud.
Okay. Um, yeah. So a scenario would be like, given the list up here, like randomly given some numbers from that list. You would start creating your heap. And so let's say the first number is 8, second 3, 2, 1, 7, 1. We're missing 6, 14. Yeah. So given this, your tree would start where you would create 8, and then it would have 2 children, which are empty. Then, let's say you have 3, you can just put it to the left. So you get like 8, 3, empty. Then you get 1, and here is where, oh sorry, I've already violated it. So you get 3, and what you want to do is make 3 the parent. And then you get 1, you want to make it the parent. Oops. So that's like a rotation.
This is where you want like an iPad to connect as a tablet.
Yeah.
Like a drawing tablet.
Yeah. But look, it's got the rotation thing.
Okay.
So were you following my insertions?
So explain the.
Okay.
So you're saying insert in this order.
Yeah. So you're randomly
You got
getting the
8.
numbers from that list. You start with 8.
3.
With the 3. 3
I
is.
don't know if I call that rotation.
Well, let me.
I think that's more bubbling.
True. Yeah. It's not really gonna recursively rotate other things as well, and yeah. So like this doesn't have any children, but if it did, maybe you would have to move its children. So in a way, it's like doing that rotation as well. I can't see it right now.
I can kind of see it in my head, and the rotation involves 3 nodes that rotate, and this does not involve 3 nodes in a triangle rotating.
Yeah, because all you're doing is swapping.
Exactly. Yeah. So that's the sort of bubbling.
Right.
Low values go upwards.
And there's like 2 potential swap solutions. Okay. Yeah. There's the 2 potential swaps, right? Like you would swap left and then you would check right to just see, is it smaller? Because if it is, you would swap that one. And then you would need to go down that tree if, yeah, so I can come up with a scenario there. Do you know what I'm talking about?
Yeah.
So there is like a, okay, I want to use this term, depth first search or breadth first search, and I can't explain which is the right one. So maybe go into that.
Well, you want to iterate over the 2 children. That's like breadth first search at a single node level.
So let's actually like officially define that. So it's pretty clear that if the child is smaller, you have to like go down its children until you find the correct spot in which you want to swap. So it's just finding a potential child such that if, say, this was a big number, 8, and then your children is like 1, 2, and then 3, 4, whatever, you have to scan down that list. Down those nodes until you find a spot. But like, there's potentially multiple places you could be, right? Because if you favored the left-hand side, you would potentially find a spot quicker before you went down the right-hand side. But there could be an option to place yourself there as well. So in doing so, you need to decide, I guess, a bias towards like searching left to right. And it kind of makes sense.
Typically, they don't, I think.
Yeah, because of the fact that you're kind of like doing everything left to right, the way you represent your arrays left to right. I'm just saying
I think typically from memory, insertion doesn't start at the top. It starts at the bottom.
At the bottom, yes. Yeah, right. And that would make sense because you would have to do less
it's
swaps.
linear basically. That's why it's log n, is because you only go as high as the tree. And by always inserting from the bottom, you ensure the tree is balanced as well.
I was kind of indirectly going through the mind map of like what you would do, and I did the top down, but like it's pretty clear that's not efficient because you would. What would be
You would
the
end up with
complexity
an
there?
unbalanced tree,
And
unless you have some biasing,
And let's have a quick think. Like, what's the complexity if you did that?
I think technically it's still O log n. Oh,
Really?
wait, but worst case, I guess if it was always going on the same side, it'd be like linear.
Yeah.
So it's like the worst case versus the like norm or expected case, I guess, if it was balanced.
Yeah, it makes sense that if you start from like an n node, well, your worst case still could be n, right? If it was like a really unbalanced tree.
It would be log n because your tree would always be balanced.
So it hinges on that you have a balanced
You'll never
tree.
get a like completely left tree.
Yes, because the insertion method would stop you from doing that.
The insertion method, you could say, is kind of like a breadth-first search. It's going along before it fills up an entire layer before it moves on to the next. That's very similar to breadth-first search traversal.
Yes, right. Okay, so let's rejig that. So we were rejigging it such that the insertion actually happens at the bottom. And so the start would still start with 8, right? Because there's only one. And then when you inserted 3, you start at the bottom. So because of the size is 7 big or whatever. So 8, 3, 1, 7, 10, 14, and then we'll just have that as the null value. So you would actually start here, right? Like you implicitly need to check whether your end is null, and it's null. So you would go to the next one. It's null, so you would go to the next one, and then you would insert at the very top of the parent. So the number of steps you have to take would be like how many levels you have, which is the log n part, right?
In the array form, it's where you've got the list and the size of the list, the length of the list. You know exactly where where to insert. It's like O1.
But don't you still need to check whether things are empty though?
No, because you're always filling from top to bottom, left to right. Because it does in that order, you know that the bottom rightmost node, which is going to be the next item in the array,
okay, right.
is always going to be the next.
So the key thing there is that you know this is the first one. You implicitly have that information.
Yeah.
Okay.
Implicitly, because it's inserted in that way, and always in that way, it maintains that.
So you have I'm going to say a pointer to which level you're at.
And with this representation, you don't need to represent null either. You don't need a stood optional representation.
Yes. Yeah, that's a really good point.
Without that, this heap implementation would be quite different. If you had to search for an empty node, that's like n. It could be anywhere.
And that's kind of what I was doing at the very beginning. That
I think
does
this
seem
array
like a different
representation is like where the optimization comes from, the fact that it can be represented this way.
Right. Yeah, I see.
Can you hear the rain?
Yes, I can. So you know which level or index, All right. What about deletion? So in terms of deletion, do you also get that information, like which index you're gonna update?
So it's not quite deletion. It's pop the minimum, remove the minimum.
Oh, okay.
And I can't quite remember the way to do that.
So what's unfinished though with insertion is that we have to rejig the thing. And to rejig it, when you've inserted 3 here, all you need to do is look up to your parent and check whether your value is greater or smaller. And then if it is, you just keep going up until you, yeah. So popping the minimum would be always popping the top. And when you pop the top out, then then basically you need to do a check of your children to see which one is smaller. And based on that, that node will go up.
So I was going down that route initially. It's like, oh, we bring our children up. But that has a problem, right? The node you end up, like you might end up with a gap somewhere on the bottom row. And that's not good.
Yeah.
You want the bottom row to be all on the left.
Yes. Yeah.
So if you, after removing the middle node, the root node, if you put the last node up there and then shuffle it down, you've preserved your tree shape. So it's got this like everything's top left line.
So given how big the tree is, there'll potentially be, in terms of its size, either completely filled or not completely filled. And you just have to find...
This rain is really loud. Let me close it off. It's really pouring out there.
So am I right to say that the scenario that you could be in is that you have a tree that's completely filled and you're popping the top? And when you do, you want to take, the last element of size, and minus 1. But there could be a case where it's not completely popped, right?
Sorry, case where what?
It's not completely filled out. And in that case, you want to take whatever is the biggest. So do you have to do like a search from the end to find?
No. So when it's not completely filled out, the last row, all the nodes are on the left. So you can just take the rightmost node.
But to find that out means that you know how big the heap is, right? So is that implicit?
Because you've got your array length.
Right. So so that's something that we have to keep track of.
Maybe we should actually implement this array representation of the heap.
Yeah.
Like, it doesn't have to be in code; it can be in this JSP.
Well, that's why I was saying, like, what's what are we implicitly storing and keeping? And it sounds like
So
the
just
size
draw
of
out
the
a binary tree with some values,
yeah.
and then let's write out the equivalent array representation of that.
Mm-hmm. Okay, so I'll just keep what I had then. This one. And you want me to draw out the tree. So 1, 3. Oh. Yep. There's my tree.
Yeah. So if you rewrite it as an array,
Mm-hmm.
what does that look like?
Like this.
1, 3, 5, 6, 7. Yeah.
Oops. But to my original question, which I don't think you answered, we're constantly storing the size of our array.
Yes.
Okay. So that I didn't actually note down.
Uh-huh.
And I'll just say capacity is 2 to the power of n minus 1. Yeah, so we're at full capacity, so it's at 2 to the power of n minus 1.
You know that full capacity. Oh, sorry. You mean the array is full?
Yes.
I mean, it's always going to be full. The size is how many elements there are.
No, that's where I wanted to distinguish the capacity versus the size, because there could be like this, where there's no 8, right?
And so the size would then be 6.
Yes, correct. But the capacity is 2 to the power of n minus 1.
No. The capacity is infinite. You can keep adding nodes.
Yeah, true. What
Like
I
just
meant,
like with this tree, the tree's capacity is infinity. You just keep adding nodes. Same with the
yeah,
array.
true. I guess I'm thinking in sort of fixed size array, yeah, like C level type stuff.
Yeah.
And I was
That's
like
kind of separate to
fixing,
the algorithm. Like, yes, you
yeah,
can have
true.
some limit to your fixed array,
Yeah, right.
but
Uh,
that's like extra
yeah,
resource constraints to consider
but
separately.
in fact, what you would do is like have a much greater capacity, and then your size could just keep growing till that point, and then you would, create a new array that's like double. That's like typically how you do it, right?
This is starting to re-implement std vector.
Yes, yes, yes. Okay, so the size is not like the fixed size that you can't go beyond. It's
Yeah.
just how big it is currently, and that fairly makes sense. Yeah, so if the size is this, which is 1, 2, 3, 4, 5, 6, then if we pop this one, our size will be 5. And we want to potentially not have gaps, as you mentioned. So if we take the index 6 element, index 5th element, and put it at the top, then we would swap 3, and then this would be 3, 14, 5.
Sorry, I'm a bit lost here. What's this 6 and 5?
Oh, sorry. This is just me drawing out what the size is.
Oh, okay,
Yeah,
size. Yeah.
yeah, size. And so to get the actual 14 value, you would just index the fifth element
Yes.
and, n minus one, and
So
then you
the
would
the
put that at
sixth
the
element,
top.
index 5.
Yeah, sorry. Are we talking indexing as zero base? Because that's what I meant.
When you say sixth, that's like one based.
That's true, actually. Yeah. And then, yeah, as I was saying, 14 going to the top. You do the swap with the leftmost. So 3, 5. And then with this, you would swap again. 14, 7, 10.
I guess this 14 that you're sinking downwards.
You want it to be here, though,
I
potentially.
don't know. It probably doesn't matter which direction it goes.
Yeah, I just picked a direction. So, like, I'm going always leftmost.
I guess the only important thing is that whichever one it goes down must be smaller than it. So one of the children could be bigger.
Yeah.
That is that possible? I think
Sorry,
that's possible. Yeah.
what's the case then? Like, can you?
So you could have a tree of like one, uh, 100,
Mm-hmm,
and then two,
mm-hmm,
and then under that like 200, 200,
mm-hmm.
300, 300. Oh, sorry, 200, 200, 50, 50. Sorry, under the 100 is 200, 200,
Oh, okay, right.
and under the 2 is like 3, 3.
Yes.
So if we popped off our 1 and we put 3 up there, we wouldn't be able to swap to the left.
Yeah, but is it still no gaps? That's the main criteria, right?
No what?
No gaps. So no like
Yeah, there'll never be a gap because the tree is
you're always
already
choosing the
in a
last
gapless state.
one, and that would propagate. Um, like you would never get the swap in something that's already gone. So because it's not there, it has to fill in
Well,
something
even if
that's
you
the.
kept swapping until you hit the end, like you don't change the shape of the tree.
That's what I
None
mean.
of these swaps change the
You
shape of the
force
tree.
the shape to be this because you took that element.
Yeah,
Like that's
yeah,
the
yeah.
that's the
And
reason.
you'll never swap into a gap, for
Mm.
instance. So yeah.
But the other APIs of like searching and finding, are they exactly the same? So we've said that the deletion is this method, right? So if we calculate what the log O big O complexity is, then I would say it's log n because it's
Mm,
just based on one, yeah, swapping down one path of the tree, which is going to be a
yeah.
hard, be in, yeah. So we said the size could be 2 to the power of n minus 1. And so to search, you're dividing that. Not dividing it, but you're inversing that, which is log n, right? And is that the right? Did I describe that correctly? No, I'm not sure if I am coherent when I talk
Yes,
about stuff like that.
division. Yeah, it's very dividing with this tree. It's like
Well, the dividing
it's
is
kind of
really
like
more in like the divide and
sorted
conquer,
lists.
not actual division.
This binary, this heap binary tree makes you think of like if it wasn't a tree, it'd just be a list of sorted numbers. Um, and somehow with every step we like divide it. We divide it into two separate problems at every layer. And because it's like just an ordering, a strict ordering from bigger to lower, but lower to bigger.
Hmm.
Um,
But
yeah, I think dividing is the right way to. It's hard to describe why, but I think this dividing is the right word.
it is only comes up because it is a divide and conquer when you go down one of its children and
Yeah,
you go down that.
instead of going down everything, you go down half each time, and there
Hmm.
you get the login.
Yeah, but it's not division in the in the mathematical sense. Like, well, you are kind of dividing by two, but
The search space is being divided by 2.
yeah. So
I think that's what they mean when they say you divide the problem.
actually, yeah, that's true. Um, so we got insert, we have delete, we want update. So updating, what would the API look like? So you've got like a value that you want to update, like given 3, you want to update this to something, right? So 2
Yeah,
values as parameters.
I guess you swap upwards and you swap downwards.
So you wouldn't go finding that value, inserting it, and then doing the swaps.
I think you would need to have some kind of mapping of where that value is.
Yeah, but that
Because
means searching,
if you're
right?
updating a thing, that means it must have an identifier. And so you'll need an identifier from like the ID to where in the array it is. I think that's necessary.
You don't think that you can just search? Because,
I mean, how are you updating an item if you don't know where it is? You must have an ID for it.
well, if you do, that means you're storing that in memory, right? And let's say these heaps are bajillion line, the size is really, really big. You're not going to store all that potentially. You're going to search for it, maybe. It depends on the
But then you're
problem.
searching a billion things, like that's linear.
But
You have no clue where it is.
yeah, true. Um, there is an order that is based on the tree that
True.
you could potentially, as we said, divide the search space, maybe.
Unfortunately, this one doesn't divide the search space, I think. All
Well,
you can know is when, like, so your value, say it's like 6, and you
yeah,
start seeing children of values 20 and 50. You know
yeah,
it's not down there.
yeah,
So it terminates early. It can cut off early. But you still got to check each side.
yeah.
Because
So
it
you
could be down either one.
you need to potentially just go down one of the nodes, and you'll also potentially realize that you can't go down this pathway and have to go back, right,
Yeah,
to the other side.
yeah.
So yeah, your worst case for searching would be every node, potentially, if you were to do it from the top.
But in the case of Dijkstra, where I believe you do have to update values, um, you you would keep a mapping because searching the whole tree is now turning it into a too expensive
Hmm.
n log n operation.
Is it n log n to search that? Not worst case n?
It's n plus log n, so it's just n, I guess.
Yeah. Yeah. So the fact that you have to go down one side and then potentially go down the other.
Yeah, that means your worst case is like every single node.
But how is that n plus log n? Because isn't that just
The
n?
log n is the updating part,
Oh, right. Yes. Yeah.
fixing up the tree.
So that's n, and then fixing it up would be log n, as you said.
Yeah.
So a mapping would make sense, um, where you have like a map of which index for a specific value.
Hmm.
If you have that mapping though, you could represent that actually as like you don't want to search another array for that value just to find the index, right? That
No.
doesn't make sense. You would just have something where you can, like,
Ideally, your IDs are just array indices.
mm, So the
By
API.
array indices, I mean a different array to this one.
Yeah.
A separate mapping array. Yeah.
So, so if the indices are the mapping, so you would have like 0, 1, 2, 3, 4, 5, 6, however big your array, your size is, and then you would store your values here. No, that doesn't make sense.
So the index of this array would be the ID of the item, and then the values would be the index in the heap array where they're located.
So if you've got these values, you're saying the index 3, let's say, would
Yeah.
map to the index value that you're in
Sorry,
here.
that 3 that you wrote, is that the value or is that the index?
Sorry, so it's like 0, 1, 2, 3, yeah?
Yeah.
And then this guy would have like the index, so 0, 1, 1.
Yeah.
But
That's
then
right.
if your values go really, really big, how do you, like, what are you putting in here, like 1 and 2?
If your values go really big.
Yeah. Like, what are you putting here anyway? Like in this case where you've got index 0, index 1, index 2, index 3.
I mean, yeah, this array is going to be size n. That's fine.
Size n of the number of numbers, like the same size of the
number of nodes.
Yeah. So in this case, 1, 2, 3, 4, 5, 6, right?
Mm-hmm.
So sorry, you're saying the mapping is the index to the other index.
Yeah.
So
you know where in the heap it is.
So again, then does that mean you've padded out this array?
Well, both of these arrays are dynamically sized. Like the number of nodes is changing, right, as you insert and delete.
No. My question though is in the index array to the other index.
Yeah.
I'm still confused by your representation. So can you just maybe spell it out?
So these nodes have an ID.
Yeah.
And these IDs ideally can be used as array indices. Mm-hmm. So they go from 0 to n minus 1. And because they can be used, because they're just array indices, looking up their value in this mapping is 01. You just use the ID as the index into this mapping array.
So that's why I'm saying like a really layman version of that would be the index 3 maps to index 1, but then you've got 0 index, 1 index, 2 index, and then 3. So you can't do that unless you've got these like other indexes that are completely empty or something.
Sorry, say again. It's the rain is really loud.
So if you created some array that is as big as your biggest number, let's say, plus 1.
It's as big as there are nodes. It's the size n.
Yeah, and that's why I can't.
It doesn't matter what the node numbers are. Like 14 doesn't come into this at all.
Okay.
So they need to have IDs which are separate from their value. Like you're updating a node.
Yeah.
You'll use its ID to reference it, and then you'll change its value. It doesn't make sense to change its ID.
Okay.
That's right. Very different.
Okay, so when you assign something, we just give it some ID. So we could say like A, B, C, D for each one of these.
Yeah.
As they're being added. And when A is added in the index map, we just put it where it correlates to the index of the min heap, right? So so is there an ordering though for these IDs? The IDs can be whatever, right? They're not like somehow ordered. That doesn't make sense.
So in Dijkstra, it's kind of fixed. N is sort of fixed up front.
Yeah.
It's the number of nodes in the graph. And that's easier to work with. Every node, you just give it a number from 0 to n minus 1. And that fits nicely into this array. If it's more dynamic, then it's more complex because like if you can keep adding ones, like it keeps growing and shrinking and whatever, then you have the problem of like you probably want to reuse values that have been deleted to avoid wasting space.
So can
and in that case, you might end up using a hash map or something.
Yes.
But in the case of Dijkstra, where it's a fixed number for the entire problem, this is really efficient. You can just use an array.
And in that case, it's also ordered the IDs, right? Because it's just
the order doesn't really matter. You can rearrange them.
Okay.
Nothing changes.
Okay, so if that's the case, let me assign like a char to each one of these, like I did A, B, C, D for left to right. Okay. For these numbers that are going to be added.
You mean instead of numbers, use letters?
Yeah, let's just say since they can be any arbitrary mapping.
We still need them to be ordered. So I guess like letters greater in the alphabet are bigger.
So that's what I was saying. They have to be ordered.
Yeah.
And so if you're creating some ID, the requirement there is that the hash or whatever that you make is ordered according to something. And the
IDs don't need to be ordered. The values need to be ordered.
So when you're, say, picking a random value.
Sorry. Do you mean in the array mapping?
Yes, in the array mapping to the index.
Yeah, well, it's more than just ordered. It's like it has to be from 0 to n minus 1 specifically.
Yeah, so that the map that you make has to somehow fit into that scheme, right?
Yeah.
Where
if you have a fixed number of nodes that you know up front for the problem, you just assign them all a value.
Yes. But if it's dynamic, as you said, and growing.
Yeah, then I would probably use a hash map instead of an array.
So let's I want to explore that a bit more.
So the problem with the array is, say you've added 100 nodes, and then you remove 100 nodes, so now there's no nodes, and then you add 100 more. Do you recycle IDs? Like you kind of want to reuse those spots in the array, but like that's complex to keep track of what you've used, what's currently in use, and what's available. This is like heap allocation problem all over again. Fragmentation of gaps in memory that's free to use or currently in use. The ID space now has this arbitrarily complicated set of existence in use or not in use.
Yeah, I guess we never did like Dijkstra's dynamically adding more nodes, right?
Well, yeah, that's not really part of Dijkstra.
Yeah, because every time you do, you then have to re-Dijkstra it to figure out the new configuration.
I don't know if we've learned Dijkstra as like an update on an existing Dijkstra output, but that's something worth like would be interesting.
Yeah.
How to rewrite Dijkstra so it can be sort of updatable, like as the
Mm.
graph changes.
Because
With
it kind of touches on this problem, right? Because how would you sort of recycle the heap map that you're using or
Mm.
something?
And yeah, you would have this problem of like, okay, we got a new node, or okay, we deleted the node. What happens
Mm.
to our ID map?
Well, my battery's about to die, so maybe let's end there.
Okay.
We'll leave the implementation to next one.
Yeah. Yeah,
GG.
but this was good to cover heap. Like, it's a simple idea, but you know, there's a lot to it actually.
Till next time.
Yeah.